Now let's imagine we have a continuous variable and a categorical variable. Generally speaking, our dependent variable, the one we're really interested in explaining or understanding, is the continuous one, and the independent variable is the categorical one. It's possible that might be reversed, and I'll show you an example in a moment, but it's pretty uncommon. So for our purposes, let's just assume we're always more interested in the higher order variable, meaning ratio over interval over ordinal over nominal. In the simplest of these scenarios, our categorical variable is binary, or can be collapsed into two groups, and therefore we want to use a t-test. There are a few different versions of the t-test, but at core they are comparing the means between two groups. Visually speaking, this would be like comparing the distributions between two groups. We might put two histograms overlapping each other, or two box plots or violin plots side by side. The most common form we encounter is the independent two-group t-test. In this case, we have two non-overlapping groups, and we want to see if there are meaningful differences between them. The most common textbook example you'll see is the relationship between sex and body size. Essentially, if we divide the world into males and females, is there a difference in terms of height or weight or things like that? And the answer is generally yes. There is a statistically meaningful difference in the average heights of males and females, as you can see on this particular graph. Note that we are talking about averages, not absolutes. We can see clearly from this graph that there is some level of overlap. It is entirely possible to find individual women who are taller than individual men. That does not invalidate the general trend that men tend to be taller than women. What I want you to recognize is that most things we will measure have some level of variation to them, and we can and should be mindful of that, even while we talk about what the aggregate picture shows us. Another common form, though not one we often encounter in sociology or political science, is the paired t-test. This is most often seen in pre-test, post-test scenarios, so very often the social science field that uses this is psychology. The idea here is we have values on the same set of units, usually people, both before and after some intervention or activity, and we use the t-test to see whether the intervention had any impact. So what happens if our categorical variable has more than two groups? Well, we could turn to ANOVA, which stands for Analysis of Variance. We might imagine our categorical variable is something like race or religion. The key limitation of ANOVA is that it doesn't tell us which groups are different from each other, just that at least two of them are significantly different. You'd have to run further tests, probably sets of t-tests, pairs at a time, in order to clarify. So as such, we don't often encounter ANOVA, so I'll show you how to use it, but we'll focus primarily on the t-test. Here are some examples. In our last analysis assignment, we used chi-square to look at vaccination status and age. Chi-square is for two categorical variables, so we bucketed age into categories. But we have access to age as a continuous variable, so we can flip that with a t-test. Effectively, we're asking, is there a difference in the average ages between those who have been vaccinated against COVID and those who haven't? And if that sounds a bit odd, it is, because we're treating age as the dependent variable. Obviously, whether or not you've been vaccinated is not going to have an impact on how quickly you age. But this is one of those rare cases where this sort of modeling still works. When we looked at this by age bracket, we found there was no association between age and vaccination status. But when we allow age to remain a continuous variable, we find the opposite. The average age of those who received at least one vaccine dose is 51, while the average age of the unvaccinated is 45. And that difference is statistically significant. This, plus the graph you see, suggests that our chi-square analysis might have shown a different outcome if we had chosen different age bracket divisions. One last example. Let's look at how food sufficiency, an ordinal variable, intersects with amount spent on food, a ratio variable. Since our categorical variable has 4 options, we'll use ANOVA. And we find there is a meaningful difference in amount spent on food when broken out by food sufficiency. Interestingly, it looks from this table like people who are food insecure are actually spending more on food than those who are food secure. This is an example of what people mean when they say it costs a lot to be poor. People who are food insecure often have limited access to quality food, and typically the food they do have access to is at a marked up price, so they pay more to get less. If we wanted to delve into this further, we could start collapsing categories, or we could start setting up a series of t-tests to gain further nuance on the story here. That's actually where we'll pick up in this week's analysis assignment. You're going to get some practice with minor data manipulation as well as running and interpreting t-tests. You'll collapse the food sufficiency variable a few different ways and further explore this relationship between food sufficiency and food spending. The command you need in R to do this is t.test, and though we're not going to worry about ANOVA in the assignment, in part because it's just a little bit harder to interpret in R, if you're curious, that command is AOV. And we will walk through this in person as well during our Zoom class session.